So we've been having this discussion about limits, but really, so what? Why do we actually care about this weird limit thing that we've dealt with, but it's just been with these functions and it's been in more of an abstract setting, right? So today I thought, let's try to see how do limits actually help us in the real world. So I wanted to pick up with an example that we got to see yesterday, which was with Newton's law of cooling. The temperature of the cup of tea after t minutes is given by this equation here. Before we get to this idea of limits, I want us to remember when we started out pre-calculus, I said we're going to talk about functions. And functions are really important because these are the way that we describe physical phenomena of the world. Right? So this is a function, it's an exponential function, we've talked about exponential functions theoretically. This is a physical context for when it comes up. Also, for the record, 170 degrees Fahrenheit is the recommended water temperature for steeping green tea. 4 minutes is a little long on the steep time though. Anyway, so with doing this function now, what I want us to first do is just focus on graphing a function. I want you to graph it on your whiteboards, but before I turn you loose to do that, what are important characteristics we need to show on that graph? Okay, so we need to worry about asymptotes. In this case, what type of asymptote would we have?
Horizontal.
Horizontal asymptote. So you want to make sure to have a horizontal asymptote. Is that the only thing you're going to want to make sure to highlight on your graph?
Y-intercept.
And a y-intercept. Okay, makes sense? So I'm going to give you 30 seconds to a minute on your whiteboards. Make sure to get your horizontal asymptote, y-intercepts all clearly denoted.
Oh yeah, no, that's right though.
Alright, and now on 3, I want you to get ready to go ahead and hold them up so that way I can just make sure that we're okay with everybody. So 3, 2, 1, let's do a reveal for what you have. And I'm seeing most people have a graph that looks something quasi like this, right? And this is what we would expect. This is what we've seen before. This should feel like review. Now I have a question. This is our model, and the graph of our model. According to our model, will the temperature of the tea ever reach 72 degrees Fahrenheit? Why or why not? What do we think? Okay, so I hear yes because it's the room temperature. How many people think yes because it's the room temperature? So, some people, okay, you can be honest, that's okay. Was there anybody who thinks no? Okay, why do you think no?
Because it approaches 72 as it approaches infinity, but it's never actually going to get to infinity, so it's never actually going to get to 72.
Well, I think you meant it's approaching 72 as it goes off to infinity,
Right.
but it might not ever actually reach as we go off to infinity.
Right.
Okay, so let's try to phrase, does this make sense so far? Was there a question?
No.
Okay, so let's try to rephrase this and figure out an answer for sure. The physical relevance question is this. And we've been talking about these in a physical context, that's when we care about this. But to actually reach an answer, we need to talk about this in a more theoretical, mathematical, abstract concept. So, what's the abstraction about this? Well, I want to know if this function ever equals 72. I want to know, do we ever touch or cross our horizontal asymptote? We can mathematically show this to ourselves. And so to do that, that would mean we need to take 72 and set that equal to our function. All right, so we never reach this. Does our model ever reach 72 degrees Fahrenheit? Excuse me. So no. Model never reaches 72 degrees Fahrenheit because it never touches its horizontal asymptote. Does that make sense? Question?
So we had an actual cup of tea, and we left it in a room that was 72 degrees. You're trying to tell me it would never reach 72 degrees.
Okay, so this is a good question. This is actually exactly where I was going. Our physical understanding of this, would the cup reach 72 degrees?
Yes.
Yeah, it's going to reach 72 degrees. My point here is to say, according to our model, so this is what we're modeling, right? Does the model ever reach 72 degrees Fahrenheit? No. You can get the model as close to 72 degrees Fahrenheit as you want, But theoretically, talking about it in this concept, we're never going to get to 72 degrees Fahrenheit.
So is this a wrong model then?
So the question is this a wrong model? What do we think to that?
Yes.
Yes.
Okay, so some people say yes.
Well, like, on technicality, yes, but like, if you're trying to like make a function out of something, it's probably the closest you can get.
Okay, so ultimately we have questions about whether or not this is a good model. That sort of a question is something you should always be asking yourself in your other classes, in your other work. Math courses, we get to work with whatever models we want, just play and practice with functions. But in the real world, when you guys are actually dealing with functions, you should always be asking yourself, does this make sense? Is this a good model? Ultimately, I would say this is a fine model, but you want to make sure you're aware of what your restrictions are. Okay? So what does all of this mean and deal with in terms of limits? Let's calculate the limit as t approaches infinity of my temperature function, which we could do graphically based off of what we've seen here. I want us to go ahead though and take a moment to review our limit laws. So I'm going to go ahead and I'm going to project those here. And let's take a look at calculating our limit. So if I want to use limit laws for this now, I have a summation, which means I can split that up into two separate limits. This I can't really break apart anymore with my limit laws. But now here, I have a constant times a function. So a constant times a function means I can pull the constant outside of my limit. So that gets me plus 98 times the limit as t approaches infinity of e to the negative 0.06 t. Are we okay with all of this so far? All right. Inside of a limit, something I want you to be aware of, algebra still works. Any algebraic techniques you would normally use still apply and are perfectly valid. If you have something to a negative exponent, how can you rewrite that? So for example, if I give you x to the minus 1, what's that the same as?
1 over x to the 1.
Right? So a negative exponent means you can flip where your whole thing is. I want to use that idea here. So I have the limit as t approaches infinity of 72 plus 98 times the limit as t approaches infinity of 1 over e to the 0.06 times t. Okay? Now, let's actually take our limits. So far we've not actually taken our limit. When you take the limit, though, you're going to stop writing your limit notation. So if I take the limit of 72, are there any t's in here? Okay, so as t goes to infinity, does this quantity change?
No.
No, so that's just going to be a 72. Here I get a 98. That's still just a 98. But now if I take the limit, so this I'm taking the limit as 1 over e to the 0.06 times t, and I'm letting t get really, really, really large. So the idea with limits is you're approaching this value. So if we think about t approaching infinity, getting really, really large, 0.06 times a really large number is going to be what? Large or small? So 0.06 times infinity, or times a large number gets large or small? Large. If I do 60 million times 0.06, I'm still getting a large number. E to a large number is going to be large number, even larger. So then if I'm dividing by a really large number, the overall fraction is getting smaller. And it's approaching a smaller and smaller and smaller number. This limit of approaching a really small number like this, we say the limit, if you examine the behavior of this function, it's approaching 0. It doesn't actually need to equal 0, but it approaches 0. So I get 0. 98 times 0 is 0. So now I get just 72 degrees Fahrenheit for my overall limit. Okay, so how does this relate back to our model? Well, it matches up with our behavior here, right? That we actually reach our 72 degrees. Okay? So a limit of our function never reaches 72 degrees. But by taking a limit, we're actually able to get to our 72 degrees. The big takeaway, a limit doesn't necessarily always care about the function value itself, it cares about what you approach. Okay?